Hello. Today we'll talk about the PyData project, which aims to compile Python and scientific Python packages to WebAssembly, so it can be run inside a browser. A few words about myself. So I'm a data scientist in Paris, mostly working as an independent consultant, and I'm also a core developer at scikit-learn and the PyData projects. So the plan today is that we'll start by introducing Pyodide and discuss its features. We'll then look through different user interfaces that are available for Pyodide, and we'll also discuss the implications of running Python on the front end. And then we'll consider the use case of deploying machine learning models with Pyodide, and we'll conclude finally with looking at the current challenges and things that still are planned to be developed in the near future. So first, what is WebAssembly? So WebAssembly is a binary instruction format for a virtual machine. Initially, it was developed to run inside browsers, but lately you can essentially run it in a different environments. So you just take this WebAssembly file and you can run it with the proper executioner anywhere. So its features, it's portable, so it doesn't change depending on the architecture. It provides near-native performance, and it is sandbox, same as JavaScript execution inside the browser. So a typical build pipeline for WebAssembly is as follows. We take some C++ files, we compile them using the mscripting toolchain. This produces WebAssembly modules. And then we add some JavaScript glue code to load those modules on a HTML page. And then finally, we can render them in a browser. So since the Python interpreter is essentially written in C, we can do the same thing for the Python interpreter. And that's what the Pyodide project does. So we take the CPython 3.8, we build it for WebAssembly, and then now we are able to run Python code inside the browser. So additionally, other important parts of Pyodide is that we build the main scientific Python packages. Here, there's a few, but the full list will be shown in the following slide. So once we have those packages with WebAssembly, we can use them from inside the browser. Other important modules are the micropip package, which allows you to install pure Python wheels from PyD. And there is some interface that allows you to do type conversion between Python and JavaScript. So meaning that if you have an object in Python, you can expose it in JavaScript and use it from JavaScript and the other way around. Of course, trying to run Python in the browser Pyodide is not the first project to do that. There have been a number of other open source projects. So for instance, we can mention PyPy.js, which builds PyPy using ISM.js, which is a technology that was before WebAssembly. And here it's for Python 2. So this project is no longer maintained. Then there is the Britain project, which implements a Python 3 interpreter using JavaScript. And it also includes parts of the stdlib. There, the challenge is how can we add support for modules that use C extensions. There's also the Rust Python project, which implements the Python 3 interpreter with Rust. And because Rust has really nice tools to produce WebAssembly, you essentially can easily also build this for WebAssembly. There's also the MicroPython ports WASM project, which is a project to compile MicroPython to WebAssembly. This is fairly experimental, but it's targeted to low resource environments, or if you want to download size to be very reduced. So if you look at the supported Python packages in PyData currently, that focusing on those that require C, that have C extensions, the list is here. So we build the main like the core packages, including NumPy, Pandas, Matplotlib. Those are very reliable, and we mostly we pass a good part of the test suite of those packages. So it means that we can also run PyTest inside the PyData. Then there is scipy. Scipy is a really large package where there's a lot of things, and in addition, it has Fortran. And the issue is that there's no currently a compiler that can produce WebAssembly for Fortran. So what we do is we convert that Fortran to C. But then this works to some extent, but not for all modules. So scipy is partially packaged, let's say. And then there's also the challenge of linking BLAS and LAPACK libraries into scipy, which is also something that's still kind of ongoing. So scipy is fairly experimental. And as a result, packages that depend on scipy are also experimental, even though by this themselves they build fine because they rely on scipy. They can run into edge cases when things don't work. So those are scikit-learn, stats model, and scikit-image, hopefully soon. And of course, additionally, you can install pure Python wheels from PyPy using micropip. So micropip is just a small Python package that uses web APIs to download packages from some location. So it could be PyP or some arbitrary location. It has a very rudimentary dependency resolution. And just a reminder, so if on the right, you can see that how to determine if a wheel on PyP is a pure Python wheel or a architecture-specific wheel. So for instance, here we have, the first is a pure Python wheel. It has none-any architecture. And the one below is a manual Linux one wheel. So it only runs on Linux and on a specific architecture. So those will not work with PyData. Then, of course, this is the ideal case. So the ideal case is just install things from PyP. However, in reality, there's some modules that PyData doesn't support. So, for instance, it doesn't support supersessing or sockets. So, if those are imported at the top level, it'll fail. So it means that they have to be patched. So packages have to be patched sometimes. And in which case you have to actually submit it as part of the PyData build system that applies those patches and distributes then the files. So for C extensions, we don't really have much choice. We just include them in the PyData build system, and we have to write essentially a configuration file, build configuration file similar to that, what you would do for CondeForge. And then finally, those packages are built. So we have a JS file and data file. Those are distributed via our specific channel, and you can load them either with load package or micro. So an interesting thing is that we are able to convert types between Python and JavaScript. So meaning that if you have, for instance, a float in Python and you want to pass it to JavaScript, it will be converted as a number. Or for instance, for strings. So for basic simple types, we are able to do this conversion. For more complex types or like objects, we use either proxy objects or extension types, which essentially allow you to expose some opaque wrapper that supports a number of operators. So for instance, you can set attributes, get attributes, and the full list is provided in the documentation. So to give a more concrete example, for instance, if you want to use JavaScript from Python, you can essentially, you have this JS module in Python from which you can import JS objects, and including access DOM. So for instance, here we import the JS package module, and then we set the document title to a new value. So this means that this Python string is going to be converted to JavaScript, and then we use this proxy object to set the title. Similarly, from when you use Python from JavaScript, there is this Pyodide PyImport functionality where you can import objects from the global scope. So, for instance, in this case, we have imported the sys module in JavaScript, and then now in JavaScript you can call some attributes of this object. So in terms of performance, what do we have? So here you have a list of benchmarks, like fairly simple benchmarks that compare the native performance with the performance in once you build the package in, well, once you build Python for PyData for two different browsers, so Chrome and Firefox. And so on the x-axis, you have the slowdown factor. So 1 is native performance, and you can see that the slowdown factor is between 1 and 10, let's say. And generally, what we see is that for pure Python benchmarks, we are 4 to 8 times slower, while for C packages or benchmarks that rely strongly on C extensions, so for instance, those that use a lot of NumPy operations, we are like 1 to 2 times slower. It should be noted also that there have been a lot of improvement in performance, for instance, in Chrome lately, last year or so. Previously, it was almost twice as slow. So there's still potential to optimize this. There's still potential to make things faster by using the latest version of mscripting toolchain, etc. So now let's discuss user interfaces. So Pyodide can be used in a number of ways. So the simplest one is just to use the very simple JavaScript console that's included in Pyodide. So it allows you to, type some commands, get results, and also expose those to JavaScript and vice versa. So this is pretty sufficient for very simple prototyping. However, if you want to do more complex things, there is the Pyodide project. So the Pyodide project is essentially the project that started Mozilla and that led to the creation of Pyodide. So Pyodide initially was a language plugin for Iodide, and Iodide is an interactive scientific computing environment where you can write interactive documents and publish them and share them in a user-friendly way. So, for instance, here you have some animations where you have a panel of a tab of code and a tab of descriptions, and then you can generate interactive figures, and then you can share them. So this project, the link is provided. You don't hesitate to try it out. Unfortunately, it's a bit less maintained lately. If you go to other available projects, there is the Baston project, which is fairly new, and what it does is it's essentially a Jupyter notebook version that only uses static files, so you don't have to run a backend server. So this is a fairly recent project. So for now, it's only in French, but translation will happen soon, likely. Now, let's consider in general what does it mean to use Pyodide in all those user interfaces, or generally in Python apps that run inside the browser. So in the classical setup, you have essentially your browser that has a user interface. The user interacts with it, and then requests are sent to the server, and which in turn make calculations in some kernel. Right? So. And then if you need data is queried locally on the server, etc. In this setup where you have Python running in the browser, well, then you can move calculations into the browser, right? So your kernel is inside the browser now. And then you would only make requests to the data when needed. So what does it imply? Well, first, in terms of usability, it doesn't really change much. So you have either way you can run. You can just go to a web page as a user, and you will see calculations done. You don't have to install anything. You just have to open a web page. What really changes is scalability. So now, because we only serve static files, so you only need to serve Pyodide packages, you don't need to run calculations on the same server. You can really scale a lot, and easily. So you don't have to maintain an expensive and complex server infrastructure to serve all those users. You just have to serve static files. So, for instance, currently Pyodide has around 50 to 80,000 downloads per month, and so potentially there's a few tens of thousands users. Potential new users each month, and if we wanted to serve those users to make them use with a server-based architecture, that would be difficult. So, for instance, The binder project allows you to run Jupyter instances and scale them to a large number of users. And it's a fairly complex and successful and challenging project. So of course you can do much more in binder than what you would be able to do with PyData, because it's more let's say less experimental. But the idea is that with PyData, essentially you can just serve static files, and that scales extremely well. So what should be also noted is that packages are only downloaded once, and then they're cached in the browser. So this is also good for privacy, because you don't make too much remote requests, and also generally, calculations are run locally, so you don't need to send your data, or at least not as much data, to the remote server. A last point, which is important, is that in the case of algorithms or like some scientific code, the Python app in the browser would be just some archive of Python files and maybe some Python objects. And so this you can easily examine it on the client side. So if you go to a website that uses such an app, you can just examine what's happening, whether there's a code used, etc. And so this is good for transparency, but in other use cases that can be also a bit problematic if you want to protect your private information, or like some knowledge about what is done in the code, etc. So let's now look at the use case of deploying machine learning models in general. So in general, the classical workflow is as follows. We train some model on a machine, then we serialize it to disk. So then, depending on the framework, you would have, I don't know, for instance, for scikit-learn, you would probably use Pickle or ONNX. For TensorFlow, you would use the dedicated format. For PyTorch, another one, etc. So then you have to develop some kind of web service to so that the user can interact with your model. Then you package it in a container, probably Docker, and then you deploy it on the server. So of course, the last three steps are automated by some tools, or at least abstracted by some tools, but they're still there. So it's still something that has to happen in some way. So an interesting part is that if you look at some in the machine learning ecosystem, there have been lately some developments of tools that try to improve the model inference. So for instance, you have the ONNX project, which is a standard format for machine learning models. And you have also the inference engines that allow you to run predictions given this standard format. So for instance, you can take a scikit-learn model, put it into ONNX, and then deploy it. And you can also people have managed to also compile, for instance, ONNX to Webassembly. So it means that potentially this model, you will be able to run it in the browser without having to actually use Python. So this is good in terms of, because it's optimized, it's fast, the model is small, but the disadvantage is it's restricted to the predefined operators you have. So it's restricted to the operators that are defined in ONNX or that are defined in TensorFlow. And if you have some custom preprocessing steps, well, that can be problematic. So a side note, if you look at the current usage of what serialization formats are used, for instance, for scikit-learn, it turns out that most people seem to use Pickle. So the question is, can we just use Pickle with PyData and deploy models in the browser? So essentially, Pickle has several issues. So it's unsafe. It's very brittle to environment changes. So if you change your version of your dependencies or the version of Python, the model that you serialized before will likely not work. But the advantage is it's portable, and it's non-epic. So it means that you can always recover the Python object you serialized and look into what elements it has. So then in Pyodide, because it's just essentially Python running in a browser, what the steps to serialize to deploy a model are fairly straightforward. So you just first have to train this model in the same environment with the same version of Python and dependencies as Pyodide. So then you serialize the model with Pickle, So you get a byte object. You send this byte object to your browser, so you just load it in the browser, and then you deserialize it there. And essentially here, now you have the same model that runs in Pyodide. And then you can run inference, for instance, in JS. So generally this works. However, this is still fairly experimental because mainly of scipy packaging. So scipy is currently a blocker. So some things in scikit-learn will also not work, and then the download size is relatively large. But the idea is fully acceptable. To go one step more, you can even because you have the full model, you can even tune it or train it in your browser. So imagine you have you have some use cases where you accumulate data that's your personal data. In this case, you don't even have to share it with some server, so the model can be retrained. You can just try to tune the model locally. So the advantage is, of course, it's privacy preserving. You can fully control what's the thing you're optimizing, though, of course, the model evaluation is a bit more challenging. So to give a concrete example, for instance, I don't know how many of you search for simple Python functions in some search engines, and you get some results like this. So you get a lot of tutorials, and then you have Python 2 documentation, and then maybe somewhere at the bottom you have Python 3 documentation from the standard library. So the thing is, clearly, like at least in my case, I would like to see that as a first item. But apparently the personalized search system doesn't manage to determine that. So what you could imagine is some summary ranking model on top of like your top 20 results that will be updated as you browse, and then that will score some domains higher than other ones. So if this is like a side project idea, if somebody wants to look into it, that's I think it's a nice idea. Well, so we have seen some of the things you can do with Pyodide. Now there are still remaining challenges. So one challenge is the download size. So essentially, a Python ecosystem was never optimized for size, and as a result, you can, well, for one, have very large packages such as scipy. Even if you use just one tiny part of scipy, for instance, sparse matrices, you still have to load everything else, and this is problematic in terms of in terms of download size. If you just go to a web page, it downloads stuff you don't actually use. Then there is, for instance, the inclusion of tests in the main package. So, which is nice for development, but then if you use this package, you don't necessarily need tests when you deploy it somewhere. And then there's, of course, if you want to do static analysis of imports, it's also kind of challenging because there's like lots of import in the needs that not all of them are used, and then you can have conditional imports, and then if the conditional imports fail, something else happens. So it's challenging problem. So the bottom line is currently the minimum size to run Pyodide is around 20 megabytes. When you download that with compression, because browsers now implement compression, that's transparent kind of to the user, you get around 8 megabytes. So this is the minimum download size you have to run Pyodide on some web page. And then, of course, each package you use additionally adds additional space. So, for instance, Pandas requires 8 more megabytes to download. But still, there's some potential to optimize this download size. So this is something that's just requires time to tune. Another thing is there's clearly limitations due to the environment where you run Python. So, for instance, there are some limitations that are inherent to the Wasm virtual machine. So, for instance, the fact that you cannot do subprocesses. Initially, you couldn't do threading. Now you can, but we still haven't enabled it in Pyodide. There are no sockets. It's also a 32-bit architecture, while I think right now most Python packages in scientific community optimize more for 64-bit. And then not all system calls are implemented. So it means that You can in some edge cases you can end up with a system call that's like for a system call is, for instance, interaction with the file system or interaction with the kernel in some other way that's just not implemented and not doing what it should be doing. It's fairly rare, but it happens. And then there is the fact that if you want to interact with JavaScript has some specifics. So, for instance, it has no integer type, so it only has a number type, which is the same kind of similar as a float. Or a big integer type, so you have to make a decision how to make the conversion. There's no standard way to represent n-dimensional arrays. You can also end up with something that's essentially a valid method name in JavaScript, but not a valid method name in Python. For instance, finally is like using a finally somewhere in the Python code raises a syntax error. And to conclude, there's still a lot of things that could be improved. So, for instance, we need to work on keeping up with mscripting releases, because those releases include a lot of fixes, both in terms of size, in terms of performance, and just bug fixes. We also need to spend time on upstreaming patches. So currently, the packages that are built, sometimes they are patches to make them work with Pyodide, and not all of those patches are sent upstream currently. There's also maybe a need to implement some small parts of the std-lib. For instance, those that rely on threads and they are frequently used. So you cannot use, for instance, use the HTTP client currently because it requires sockets, but you can rewrite it with the web API. There is a challenge of how we deal with dynamic linking of Lapack and BLAS, and which in turn would hopefully improve the situation with scipy. There is also the question of general sustainability of the build system, because currently all those builds are run in the same CI, and as you add more packages, the CI gets a bit slower, so it's getting a bit more harder to contribute. So there's open questions of how to deal with that. Maybe go more towards a Conda Forge model, or try to integrate into Conda Forge, etc. There's also threading, which is currently disabled, but we should be possible to enable it, and we're waiting for a wider browser adoption. So in general, if you're interested in contributing, don't hesitate. There's a lot of things that could be improved, and we really welcome both technical and non-technical contributors. Finally, I would like to thank the team who started the Pyodide and the Pyodide project at Mozilla, other Pyodide contributors and developers, the Nexedi company, who's an open source development company in France, who funded my work on Pyodide last 1 year ago. And I would like to thank Boston Project, doing nice development work on the user interface with the Pyodide backend. So thank you. If you have any questions, please check the PyData schedule to know when the question sessions happen. Thank you.